All right. So let's focus on the ones that I circled. Uh, but like I always say, if you can stay a step ahead of me, guys, everybody got some paper out? Everybody solving these? Okay. If you can stay a step ahead of me, then that's a good sign that you know how to do this. Let's see what we got. Number 3 for the warm up. A spinning wheel steadily slows from an angular velocity of so many revolutions per second to so many revolutions per second, and it does this in 10 seconds. Calculate the wheel's angular acceleration in radians per second squared. And then question B is, what angle does it go through during this time? Right. Oh, that sounds kinematic. Doesn't that sound kinematic? Kinematic motion, right? Just for rotation, of course. Right. So I'm thinking this stuff going on right here, right? Or if you want a picture of this rotating wheel, maybe you're thinking like this picture, right? Something that, right? Oh, there's like angular displacement theta, right? It's spinning at some rate, omega, but that's always changing because there's alpha. Like it's what's it do? Is it slowing down in this case? Right? It's like slowing to a stop, right? Okay, so we're gonna use something kinematic, right? Before I plug anything in though, they gave us weird units. Did you guys notice that we have to convert the units first, right? Oh, they gave us revolutions per second, and we want probably radians per second. So number 3, I got omega initial. They gave us those 2, right, and they gave us like 3 sig figs, right? Revolutions per second, right? But we don't want that. We want radians per second, right? Right. So how are you going to convert that?
1/2 pi, right?
So 1 revolution is how many radians? 2 pi radians, right? Gives you radians per second right there, right? So that'd be what, like 4 pi? 4 pi radians per second. Okay. Right, then omega final, they said was like, well, I'll call it 1/2 revolution per second. I think is what they said, right? Okay. Let's do the same conversion. There's 2 pi rad and a rev. Radians per second. That's like, looks like pi radians per second. Okay. So it was spinning this fast, and then later it's spinning slower. It was like slowing down because of friction, possibly, something like that. Okay. And we need a third kinematic value to be able to solve this. They told us the time interval. They said the time interval is 10 seconds. Right? So there's your 3 kinematic values. Let's do a tax-VV table. Time, acceleration, displacement, initial velocity, final velocity. Of course, this is the rotational version. Right? So we know this, surprise, it's kinematic. Yeah. We're going from 4 pi radians per second to just pi radians per second. Right? We're doing this in 10 seconds. Okay. And the 2 things that we could solve for are exactly the 2 questions that were asked. What rate is it slowing down? That's that guy, angular acceleration. And what angle did it go through in radians while it was slowing down? Well, that's theta, right? Boom, boom. Right? So start with alpha. Okay, we know omega initial, omega final, and t, and we're trying to solve for alpha. Guys, which equation is that? First, second, and third? Yeah, middle one right there. Boom. Right, solve for that alpha. Right. Let's do that. See if you guys can beat me to the answer. Beat me to the answer. Subtract that. It's -3. Oops. Per second. Oops. Is equal to. That about that. Oh yeah.
Oh yeah.
All right. Nice. Are you guys getting that right there? You guys getting that right there?
Oh, I like did it all the way.
Oh, you got this one? All right. 3 over 10. Did you guys get this number
Oh my goodness, I did.
right there? Yeah, is that what you guys got? Okay. All right. And since the textbook gave three significant figures, then well, that's probably what they're looking for. Like that right there. Yeah. All right. So that's the rate that it's slowing down. Is a fraction or is a decimal? Right. It's negative. Right. All right. And then what angle did it go through? All right. What angle did it go through? Ooh, could you guys use either the first or the third? Yeah, you could, right? Go ahead, pick your favorite one. I'm going to pick the first one just because there's no algebra involved. It's all arithmetic, right? I can just plug, just plug everything in, right? It's already set up to solve. The first one is. So I choose that one. Right. All right. It's going to look like that, right? All right. How many radians did you guys get? 78.5. All right. That's what I got too. All right. Probably got the same thing then. But we're probably right. Yeah. All right. You guys get that? All right. That's rotational kinematic motion, which by AP's book also does belong to the same section. So I bet you guys are going to get some questions on AP Classroom that are, well, this rotational kinematic stuff, right? Of course, AP tends towards like conceptual type stuff, but that's how you solve it out with numbers. Right. You guys ready for number 11? Number 11, a bicycle tire has mass 2.7 kilograms and radius 0.35 meters. Guys, 0.35 meters. How many centimeters is that? 35. That's a little bit longer than a ruler, right? A ruler is about 30 centimeters. Okay. 35 centimeters. Yeah, that looks about a bike tire. I can believe that, right? Treating the tire as a hoop. Okay, now guys, when they say a hoop, they're talking about this shape right here, right? Now, here guys, everybody look up here. Cell phones away. Everybody's taking notes, right? So, I forget what the question is, but I'm gonna guess that this is probably gonna come up at some point, right? Treating the tire as a hoop. That is exactly the question. What's the moment of inertia about an axis passing through the hub at the center, right? Now, through the hub at the center is nice because that also exactly aligns with this table. They're saying what's the rotational inertia about this dashed line right here, right? See, if it was any other axis, you'd have to open up the parallel axis theorem and do a little bit more math, right? But as it's phrased, spinning about its own center, yeah, that's just mr squared, isn't it? Right? So we can do that. Let's go ahead and that first. Right, so let's get that. So number 11. So for the wheel, bike tire is very simply mr squared. They tell us the mass, this many kilograms. Tell us the radius, this many meters, and square that. So that's this many kilograms meters squared. Well, they give us three sig figs, so the three significant figures, that's what that would be. Okay. You guys get the same thing? Mr squared. Sorry. All right. That was question A. So question A, what's the rotational inertia of that wheel about its center? Question B, what torque is required to produce an angular acceleration of 0.75 radians per second squared? Okay, so question B, let's get a picture for that. Here's the bike wheel, has some radius r, right? We're gonna say that all the mass of the wheel is on this rim on the outside. That's the assumption that we made so far. That's what led to that, right? All the masses on this rim on the outside, right? It's got like all these spokes, right? And then let's see if you power the wheel, right? Okay, they just said what torque is required. Now, if you think about how a bike wheel turns, right? Isn't it true that like there's like some gear here and there's like the bike chain comes through, like something like that, right? They didn't actually mention the radius that this is acting at, right? But it doesn't matter because they're asking how much torque. So whether you actually apply a force at the edge of the wheel, let's say you're just like spinning it by hand, zoom, zoom, right? Or you have a bike chain, those would take different amounts of force to get it to rotate it, whatever angular acceleration, right? But the same torque, right? Right. Now, maybe, guys, which force would be bigger? Would you need a bigger force to spin it at the edge or a bigger force to spin it like closer to the center? Yeah, closer to the center, you need a huge force. On the outside, you don't need nearly as much force. Kind of like opening the door, right? There's a reason that the door handle is opposite of the hinges because it gives you a huge radial size, so you need a very small force to open the door, right? But they didn't even go that far. They're just saying how much torque, right? How much torque. So it doesn't matter what's coming from the chain. It doesn't matter where you apply the force, right? So torque is equal to I times alpha, right? I times alpha. It's also equal to R cross F. That's kind of what I was getting at with the other perspective, right? But we know I, that's that number right there. And we know the target alpha because they gave it right there, 0.75 radian per second squared. So let's put it all together. The necessary torque is this many kilogram meters squared for rotational inertia, and 0.75 radians per second squared, I think, yeah, is the angular acceleration. Put it together, we can figure out how much torque. All right, so the torque is, right, now, I got kilograms, I got meters squared per second squared. The radians, remember that kind of in a way disappears. You can say like, well, right. Anyway, it's gonna be 0.248. Right. Actually, maybe more simply, guys, what's the unit for torque that we've been using like last few days? Newton meters. And that'd be the torque. Right? You guys see that? Right. That's equivalent to all this fun stuff put together. Right? Just like kind of ignore the radians. Okay. Right? So that was question B. I think there's a question C. Here we go. What friction applied tangentially to the edge of the tire would create a torque of that magnitude? Okay. So they're saying, yeah, what if you put a force like right out here at the edge? Call it force. They specified a friction force, but anyway, right? Maybe it's like this. Yeah, sure, there's a bike chain and you're pedaling and that's getting it to move, right? But a torque, you need like 2 points of force at some radial arm, right? Like if you push on the door, the reason it turns is, well, the hinges are like stuck in place. That's like the counter force, right? Right. So maybe like relative to this chain or the center of the circle or something, right? See, if there was no friction with the ground, then it wouldn't actually cause a torque, right? Right. So you need a force here. Let's do R cross F. So remember, I times alpha equals R cross F. That was this whole poster right here. Right? We did this part. Now we're going to switch over and do this part. And it's all equal to torque. Right? Just like that. So I got, need more paper. So torque equals I times alpha. That's also equal to R cross F. Okay? And this we figured out already is 0.248 Newton meters. Right? The radial size, capital R, it's like a fixed R, was given as 0.35 meters. 0.35 meters. And now we can solve for what force would it result? Oh, hey, look, Newton meters equals newtons times meters. There we go. So just divide this over. point. Got that? Yeah, got that. Divide by 5. Right. What are you guys getting for your force? Yeah, 0.709. What's the unit? Newtons. 0.709 newtons. Right? Just like that. All right, and that was part C. All right, so we got ABC. All right, you guys are right there? All right. Okay, and we got one more warm-up. Okay, so we're still in the warm-up section. Right? Guys, everybody cell phones away. Guys, cell phones away. Cell phones away. All right, you guys are focused on physics. Right? Number 12. A bowling ball has mass so many kilograms and is rolling at 3 meters per second along the level surface. Okay, so they told you the mass of the bowling ball and the speed, the linear speed of the bowling ball, right? Interesting, they haven't given us the radius yet, so I haven't read the rest of the question yet, but already the gears are turning in my mind. I'm thinking, okay, the fact they gave us a bowling ball, I bet this is going to come up at some point, right? How the mass is distributed. Right? So rotational inertia is 2/5 mr squared. They told us the mass. They haven't mentioned the radial size yet. So what else we got? Calculate the ball's translational kinetic energy, the ball's rotational kinetic energy, the ball's total kinetic energy, and how much work would have to be done to bring the ball to rest. Ooh, all right. So, right. The first one I think is real straightforward. First question, right? Which is kinetic energy translational. That's just like in a linear sense, right? It's very simply 1/2 mv squared. They gave us the m and the v, so we can just pop that in. So give us a 7 kilogram ball going at 3 meters per second. Right, and then going to square that speed. Right, come up with how many joules of kinetic energy is just like for the translational motion. 1/2 mv squared. Right, I'm looking at this many joules. I should have asked you guys what the unit would be. You guys would have said joules because we're talking about energy, right? Kinetic energy. Some textbooks, some teachers do KE for kinetic energy. I've been sticking to K. AP does capital K. Okay, just got that right. Right. Now let's just translational kinetic energy. That's not considering the fact that it's also rolling, right? So what's the kinetic energy due to rolling? Yeah, that's question B, right? Now, notice they never actually gave the radial size of the bowling ball. It turns out that's going to end up canceling out the end, right? I have to think how to solve this here. Try to remember in front of you guys right now. Because, see, a rolling bowling ball. Here, let's see if we can make sense of this. K rotational. Right. Well, I'll start from the definition expression. Wouldn't it be 1/2 I omega squared? Right. You guys could have come up with that, right? 1/2 I omega squared. Right. Oh, okay. I see where this is going. Right. Guys, the fact that it's a bowling ball, I can substitute out that I in terms of mr squared, right? Right. And so it's like 2/5 for a bowling ball, like 2/5 mr squared. Okay. And then omega, guys, what is omega equal to in terms of R? V over R. You guys see that? Watch what's about to happen. So I go to my inertia, rotational inertia table, right? If AP asked you this question, they would kind of give this to you, right? So we got 2/5 mr squared for a bowling ball or any solid sphere. Okay. I think that's a good one to know, though, right? Right. I'm going to substitute that right here. 2/5 mr squared for the bowling ball, right? And omega is V over R, right? And it's being squared. So can I just call that V squared over R squared? Right? Is that what that would be? Right? And look what cancels out. The value that they never gave you to begin with. If you ever have a physics question where they don't give you some piece of information that looks like it might be important, it's probably because it cancels out. That's usually a hint that it cancels out. In this case, it does, right? So the rotational kinetic energy of the bowling ball in terms of its linear speed is 1/2 times 2/5. That's what, 1/5? MV squared. right? And interestingly, for any bowling ball, look, now you have a direct connection between its translational kinetic energy and its rotational kinetic energy. Translational, of course, is 1/2 mv squared. But the associated rotational that you add on to that is an extra 1/5 mv squared. Ooh, right? So I think what I could do is just take this and multiply by what, over 1/2 times 1/5. Right? Well, let's do this from scratch then, right? Right. So let's go 1/5 times the mass of the ball was 7 kilograms. But by the way, that's about what, 15, 16, 17 pounds, somewhere in there. That's pretty heavy bowling ball. Okay. And then it was going at 3 meters per second. That's a translational speed, but that's okay because that's what we got. And then we got to square that speed, right? I'm getting 12.6 joules. Right. Again, for a bowling ball, the ratio of these energies will always be like some set. Let's see what is that ratio. What is 31.5 compared to 12.6, right? Okay, it's like 2.5, right? That ratio will always be true for a bowling ball, regardless of the mass or the radial size of the bowling ball. Okay. And question C is, what's the ball's total kinetic energy? So K total. Well, wouldn't that just be K translational plus K rotational? Right? Okay, so I can just add these two together. Right. So 5 and 6 is 11, carry the 1, 1, 2, 3, 4, 3, 4. I think it's that many joules, is that right? I think that many. Okay. Right. And then there's a question D. How much work to bring the ball to rest? Right. Let's say it's like headed straight towards you and you got to push on it to bring it to a stop, right? Guys, how much work to bring it to a rest? Yeah, 44.1 joules, right? Right. So maybe that could be like force times distance, couldn't it? So you could be applying a force in the opposite direction for some distance. Let's say you apply a force of 44 newtons. What distance would it take to stop it? About 1 meter. Right? It's force times distance, right? 44 newtons times 1 meter. It's 44 joules. Okay. All right, guys, see that? All right. Okay, that brings us to the end of the warm-up questions, and we got about 90 seconds of class left. You guys think it's a good pause point? Pause point. All right. All right. So yeah, we got well, I guess 35 minutes of this week left. So try to make the best use of that tomorrow. And then you guys remember, what are you going to have done by Monday morning? AP classroom. Oh yeah. Oh yeah. Yeah.